Okay, so as you have seen in the previous lectures, I introduced the second law. In the previous lecture, I introduced second law of thermodynamics, and I told also that entropy is we introduced the concept of entropy, and we told entropy is a state function. And for that, to prove that entropy is a state function, we used a Carnot cycle, right? We used a Carnot cycle where we have this isothermal, which is a cyclic process, and we told that for this cyclic process, there is a quantity called delta Q reversible by T, which is nothing but equals to cyclic ds. So this is a cyclic integral over the entire cyclic process, which is equal to 0, right? So we have shown that this ds indeed is equal to 0 for a cyclic process. So what that meant is basically that if you have some sort of if you have a cyclic process, any cyclic process, say, and you start at point I, and then you are moving around, and you go to say some point F, and then again you go to I. So what we are telling is, if I start, my initial state is I and my final state is also I, then my delta S, since S is a state function, should depend on S. It should be S equal to Si minus Si, which is equal to 0, right? This is what we have proved by using a Carnot cycle, right? And right, so this is exactly, that's what I have shown here. So if you see, this is delta Q reversible by T, and this is integral ds, again cyclic integral ds, which is equal to 0. So this proved effectively that this delta Q reversible by T is a state function, and or Q reversible by T represents a state function, and that state function is entropy. And like internal energy, since it's a state function for any cyclic process, where my initial state and final state are the same, the change in state function becomes 0. Now this we have proved for the Carnot cycle, but we have considered, if you remember, an ideal gas. But it does not matter whether I am using an ideal gas or any other substance, whether it's an ideal gas or a real gas or for any other substance, the cyclic integral of entropy, of the differential changes in entropy, the cyclic integral over these differential changes in entropy will always come out to be 0, right? Entropy remains a state function whatever be the substance that we are using, right? It is exactly as much of a state function as internal energy, right? So, however, very interestingly, what we also told, that we talked about reversibility and irreversibility, right? As you remember, second law is it basically gives you the definition of irreversibility. It gives you the definition of directionality of a process, right? For a natural process, right? And it also tells you how the entropy will change, right? The entropy being a property of the universe, how will it change, right? It will always move in a particular direction irrespective of whatever process occurs, right? So that is what we have understood so far. Now another thing, if you have this Carnot cycle or heat engine, that it's a reversible heat engine, by the way, and if you look at that, we can basically define efficiency to be what? Say for example, you have a hot source from which heat is input to the engine, and then there is a cold sink where some waste heat is collected, and you are producing work from the engine, right? The work performed by the engine. So if I take the work performed by the heat absorbed by the engine as the definition of efficiency, then we can write efficiency equals to mod of W by QH. Mod of W by, because we have used we generally use this convention, means at least in this course we are using this convention, that work done on the system is positive, work done by the system, okay, or here the engine is the system, is negative, right? So we are taking work performed, the modulus of it, right? So whether it's negative or positive, it does not really matter. So the modulus of work performed by the engine divided by the heat absorbed, right, from the hot source is what is going to define the efficiency. Now, if you see that, if I use this definition of efficiency, let us further understand what does this mean. So, if you look at this diagram, you have this hot source where the temperature is TH, and you have this cold sink, the temperature is TC, and you have the engine here, right? Okay, in this engine some cyclic process is being performed, right? So, you have like isothermal compression, then you have some adiabatic expansion, the isothermal expansion, adiabatic expansion followed by isothermal compression, and then adiabatic compression. Okay, so for example, such a cycle. So, in such a case, this is your engine, right? This is your engine, and you have the hot source and the cold sink, and you see, so remember, there is one reservoir here, one reservoir here. The reservoir at high temperature is from where the heat is being transferred to the engine. So, heat input from the hot source and heat rejected to the cold sink, and there is also this work that is produced by the engine, that is mod of W, or work done by the engine. Now, you can easily see that if that is so, and also we know this relation that we have obtained for Carnot engine, that is QC by QH, okay, that is the heat rejected by heat absorbed equals to minus TC by TH. Now, epsilon is, as you see, mod of W, which is nothing but QH minus QC, because QH is plus, right? It is heat input, heat input is positive, heat rejected by the system is negative, so it is basically QH minus QC by QH, right? But we are retaining the plus sign here, that's not a problem, because QC by itself is negative, QH by itself is positive, so it is like 1 plus QC by QH, which is the same as 1 minus TC by TH, right? 1 minus TC by TH, where TC is the temperature of the cold sink, and TH is the temperature of the hot source. Now, as you can see here, the efficiency depends on the temperature of the source and the sink, right? Which is basically given by this. You can further expand to write it as TH minus TC by TH. You can immediately see that it does not, the efficiency of the heat engine, of this heat engine that we are talking about, does not depend on the substance that is used in the engine, right? Does not depend on the nature of the gas that is used in the engine, right? It only depends on the temperature of the hot source and temperature of the cold sink. Now, that one very important thing I want to tell as a corollary is that all reversible engines will have the same efficiency regardless of the material used. Regardless of the material used, it will have the same efficiency. And another very interesting thing here you can see, if I put TC equal to 0 Kelvin, then my efficiency goes to 1. Efficiency becomes 1 when TC is 0 Kelvin, right? You cannot have efficiency more than 1, right? So when TC is 0 Kelvin, you can immediately see here, right, that if TC is, say, immediately see here that if TC is equal to 0, then this is TH minus 0 by TH, which is TH by TH, which is equal to 1, right? In other cases, when TC is not 0 Kelvin, you will always have efficiency which is less than 1, right? Okay. Now, think of this, what we told is all reversible engines for operating at the same temperature, means operating at the same temperatures of the hot source, means for a given temperature of hot source and for a given temperature of the cold sink, okay, all reversible engines that have the same hot source temperature and cold sink temperature should have the same efficiency regardless of the material used, right? So, for example, think of this as this particular configuration. You have TH here and you have TL or TC is the cold sink temperature and TH is the hot source temperature. So, in this case, let us call it TC instead of TL, let us call it TC. I am using TC as the cold sink temperature. Okay, now you see, I have just hypothetically thought that we have thought that there are two engines here, one is E1, another is E2, and we have also assumed that E1 is more efficient. Let us suppose that E1 is more efficient than E2. Now, if it is so, if say let us suppose that the efficiency of E1 is eta 1, which is mod of W1 by QH, and eta 2, which is the efficiency of E2, and that efficiency is slightly less than that of eta 1, means slightly or some way less, right? It is less. So what we are talking about is eta 1 is greater than eta 2, right? So we are talking about eta 1 is greater than eta 2. And what is eta 1? Eta 1 is, so it is extracting a what? W1. So it is extracting the E1 is extracting a what? W1. So mod of W1 by QH is basically eta 1, and eta 2 is mod of W2 by QH. Now if eta 1 is greater than eta 2, obviously mod of W1 is greater than mod of eta W2. Now if you look at this, what you are talking about, if you look at it more precisely, you are actually absorbing heat QH from the hot source, then you are transferring some QL1 is rejected to the cold sink. Now this QL1, so but from the cold sink now there is a QL2 that is coming. So what I have done is, instead of using two separate heat engines, I have made one of these a heat pump. So E1 is acting like a heat pump to E2. So what is happening? So if you look at E1, so E1, so E2 is your heat pump. So if you look at this here, E2 is your heat pump and E1 is your heat engine. In this case, I have just reversed the process in E2. So it becomes a heat pump and this is your heat engine. Now what is happening? The work produced by heat engine E1 is now directly taken to E2. So work is done on E2 now, and there is also QL2 that is entering from the cold sink. Now cold sink has now become a source for E2, and you are basically now rejecting a heat of QH, or you are producing a heat QH to the hot reservoir which is maintained at pH. Now you can see here QH comes in and there is a W1 done, and this W1 is the work done by E1, and it rejects QL1 and now from the cold sink QL2 is coming into E2, right, because E2 is now acting as a heat pump and it is taking also W1, and then it is producing this heat QH which is coming to hot reservoir. Now if that is the condition, then there is one very interesting thing that comes in, because see, W1 we told is the work done by E1, right, and by E2 it is W2. Now if I now just look at the balance, you have, if you look at this, QL2 is coming in, right, so QL2 is coming in, and then QL2 and W1 produces QH, right. So QL2 plus W1 is QH, right. Now this implies what? This implies QH minus W2 plus W1 equal to QH. Why is that so? Why is QL2 QH minus W2? Because if you look at this, QH, if I look at E2 as a heat engine, then QH is the heat input, right? QH is the heat input, and W2 is the work done, and then QL2 is the heat rejected. So QL2 is QH minus W2, right? QH minus W2 is QL2. That's what I have substituted here, and you have also this W1, and you have again here QH. So basically what it tells is W1 minus W2 is equal to 0. So definitely W1 has to be equal to W2, right? Because as you can see here, so W1 equal to W2. Remember, this is a cyclic process. So even here, please try to understand, this is very, very important to understand that for any state function, for any cyclic process, the du is also going to be 0, right? However, can you tell, means whether this is something that you have to think about. See, you have a cyclic process and you have PdV. Is this equal to 0? You will see that it is not equal to 0. You look at the Carnot cycle, for example, you look at the isobaric isoporic process cycle, for example, that we looked at in the second class. You will always see that the cyclic integral of PdV is not equal to 0, but however, because see, P is a state function, V is also a state function, right? But it is a integral P dV, right? So this need not be equal to 0, right? And in general, it is the area under the PV curve, right? So if it is area under the PV curve, you have often seen even for Carnot cycle and all that it is not really equal to 0. So please have a look at it and think about it. Now, but you can see that now in this case, W1 and W2 cannot be different, they should be equal. Now in such a case, what if it is so, now you see there is a very important violation that is occurring when the efficiencies are different. See, from TH it is coming in to E1, E1 is producing work W1, and then there is this QL, and this QL is directly entering the engine E2, and there is W1 and it gives you KH. So you don't require, if the cold reservoir is no longer required, not required. The cold reservoir, the cold sink is not required in this process. Now, if that is so, the entire heat is basically getting converted to what? That's what it basically boils down to in some sense. And if you do not have a reservoir, means you should have, like Kelvin's statement was that you should have a hot source, you should have a cold sink, and there should be some heat rejected to the cold sink, right? If there is some work done by a heat engine, right? So that means that you cannot really have, in this case the statement is not valid. So that means all reversible heat engines, that means for example E1 and E2, they should have the same efficiency regardless of the material used, right? So this is something that becomes very, very important. Another thing that we told, that see, it is independent of the substance used. Why? Because efficiency ultimately depends on TH and TC, right? These are the hot source temperatures and cold sink temperatures. So this is something that you should. So efficiency, as I told you, is a function of TH and TC, right? Now remember that if you fix TC, if you want to increase efficiency by fixing a TC, which is not really, if you fix TC to 0 Kelvin, then you get epsilon equal to 1, that is one thing. And second thing, if you fix TC to some other temperature, you want to, if you want to increase the efficiency of the engine, you want to make TH as large as possible, right? Now, so again, as I told you, that note that when we proved that this del Q ref by T, that is delta Q reversible by normalized by temperature, or which is definition of BS equal to 0 for a cyclic process, we have used an ideal gas, right? We have used an ideal gas. So, but again, from the definition of efficiency and for any cyclic process, basically, by the way, if you look at this, you will see that any arbitrary cyclic process can be basically represented by a series of Carnot cycles, right? So this is something that you can do by yourself, but I will have some more elegant proofs soon that I will show, where we can basically look at whether it is ideal gas, whether it is any other substance, the idea of state function does not change. That is something that I will show in the next few, basically in the next few slides. So let's go to the next one. So as you can see here in the next, so if you go to this next idea that I want to show here. So if you start with first law, as you have seen in first law, is a law of conservation of energy, that du equals to Q minus PdV. Now this Q basically, again we can think that is the reversible Q. So but we will tell it like delta Q minus PdV, right? This is delta Q, and delta because it's a path function. Delta Q by itself is path function, but delta Q by T is a state function, remember? So integral delta Q depends on the path, right, of the process, right, the path that is taken in the process, right? However, integral delta Q by T does not depend on the path, but it depends on the initial state and the final state. Note that, right? This is path dependent, but this becomes path independent. It only depends on the initial and the final states. Now, as I told you that u is a state function, so cyclic integral of du is equal to 0, right? This is correct. This is correct. However, pdv, which is p is here one state function, v is one state function, but integral of pdv is not equal to 0, right? If you look at the Carnot cycle also, this is the end of the curve. Here also, say for example, you have say for example this process where you start with pressure of say P1, and at this constant pressure P1, so this is an isobaric process, you have an expansion, right? You have an expansion in volume for this P1, so it goes to 2 say, and then you have an isochoric process where I just increase the pressure, and then I go to again we maintain the pressure P2 and I compress it to the state 4, and then again I come back to, again I have an isochoric process by which my pressure is reduced to P1, right? So this entire process, if you see, immediately you can understand from this process that I have drawn in the PV curve that this process definitely PdV is not going to be equal to 0, right? It is not going to be equal to 0. So here, or even if you can check that Carnot cycle that I have drawn, so you can easily understand that this integral PdV is not going to be 0. Again, integral delta q, cyclic integral delta q is also not equal to 0 because it's a path function. Now, what I am doing is, I have this equation du equals to delta q minus pdv, I divide it by t. So, what I get is du by t equals to delta q by t minus p by t du. Okay. Now, again I use, for 1 mole of gas, I use the ideal gas law. So, I have du by t minus delta q by t equals to, because this is p by t is nothing but, so here you can see here, p by t equals to r by v, where r is the gas constant. So it becomes r by v dv. Now integral delta du by t is going to be equal to 0. Okay, this is something that you can prove, right? So integral du is going to be 0, and normalized by t also, integral du by t also is going to be 0, right? So that has to be 0 because the cyclic integral of du itself is 0. Cyclic integral of du by t is also going to be 0. You can actually show this if you look at this. If you just consider any cycle, you can see the change in u, and you can normalize with t, and you can see the cyclic integral that comes out to be 0. And another thing, why it is 0? It is 0 definitely for an ideal gas. Why? Because u for an ideal gas is only a function of temperature. Then I can write du equals to CVdT, right? du. So why is this 0 for an ideal gas? At least for an ideal gas, I can immediately show you. This is because du equals to CVdT, right? And because u is only a function of t, it's not a function of v, right? u del v for an ideal gas goes to 0, right? So now, if I have that, so I have du by t, which is CVdT. So this is basically integral. So integral du by t is nothing but integral Cv dt by t. This I can write as Cv dln t, right? So dln t, right? And this is ln t, so you can think of this as some state function of y. So you can see Cv dy, and this Cv dln t is definitely going to be 0, right? For the cyclic process. So because for the cyclic process, you are starting with the state I and you are coming back to the state I, and you are only looking at the at state I what is the change. So you will basically see that Cv dln t in this case is going to be equal to 0. Similarly, r dln v, right? R by v dv, I can write this as integral of r dln v, which is again going to be 0. So as a result, delta q reversible by t has to be equal to 0, equals to basically the cyclic integral of ds. Now, if I can ask you this question, please try to solve this. This is I think that will be interesting, because you can by yourself realize that delta q rev by t, reversible by t, although that is a state function, the cyclic integral goes to 0, delta q reversible by p, on the other hand, is not a path independent function. It is definitely a path dependent function. So, two things have to be understood. One is the integral pdv, cyclic integral pdv does not go to 0. Another thing, I have here del q rev by t, which comes out to be 0 here, but del q rev by p, the cyclic integral, is not going to be 0, right. So, that means it is not a path independent function. So, if I look at other substance, right, when we want to say that, okay, when we want to prove that, okay, if it is true for ideal gas, it has to be also true for other substance, and we have tried to tell that we showed that definitely from the definition of efficiency, you can immediately understand that since the efficiency depends only on the hot source and the cold sink, in general, you can immediately understand that it really does not depend on the substance, whether it's a real gas or an ideal gas, the cyclic integral remains 0. But you can also prove that. How? When you want to prove that, you take a system which is isolated. Isolated means it has, if I take an isolated system, the overall isolated system, then there is no exchange of heat or the heat or matter between the system and the surroundings, right. There is no exchange of heat and matter, and moreover, the isolated system is covered with means is separated from the surroundings by a rigid adiabatic wall, which is also impermeable to any type of mass transfer. So, if it is rigid, you can also not apply any stress over the overall system, right? You cannot apply pressure or anything. So, now in this system we consider subsystems. So, this concept of subsystems becomes very, very important when we will discuss equilibrium. So, you have a subsystem. So, you have a valve. You have a valve fitted with a valve. Okay, there is a valve here. So, valve, I think the symbol will show the circular stuff, and we put this. Okay, so this represents a valve. See, for us it represents a valve. This is a valve. Okay, now this valve is closed initially, so that we are not allowing this ideal gas and the substance to mix, right? So there is so this substance can be a real gas or whatever. So you have an ideal gas and you have another substance that is in the other chamber, right? And they are basically separated by a valve. Now, what we know is that the delta Q reversible by T for the ideal gas is equal to 0. That means for this system, so this subsystem that is denoted as 1, I know this. But for this system, it is denoted as 2, and which has a real substance or real gas. Whether this is true or not, we do not know, right? So, instead of writing the substance, this substance is basically, we can write this some substance AC. Okay. Now, if I have that, now if you see, we have this isolated system and 1 and 2 are there, and the point is you have this ideal gas, a real substance, and 1 and 2 can exchange. So, the idea is that you cannot exchange matter, but you can exchange heat. So, we are assuming this wall, the internal wall, to be diathermal. That means 1 and 2 can exchange heat reversibly. Now, if that is so, see, for example, in 1, I am telling the amount of heat that is there or absorbed or the amount of heat associated with subsystem 1 is delta Q1. Okay, that is the heat absorbed. Okay, or heat input to the the subsystem 1, and delta Q2 is the heat input in subsystem 2. So then, definitely this is overall it is an isolated system, so heat cannot be exchanged to the surroundings, right? So delta Q1 plus delta Q2 have to be equal to 0. Okay, and we are telling 1 and 2 are in equilibrium, right? So 1 and 2 are in equilibrium, isolated system, no heat can transfer. So you have delta Q1 plus delta Q2, that has to be equal to 0. Now, we are telling that the equilibrium means we are talking about an equilibrium, thermal equilibrium. Say for example, both have the same temperature. Okay, so the temperature, so at thermal equilibrium, this is also T, this is also T. Now you are telling, you divide both by T, so you have del Q1 by T and del Q2 by T. That also has to be 0. Now, but this one we know is 0. This is equal to 0. For the ideal gas, del Q ref by T is 0, that we have already proved. Now, if this is 0, if this part is 0 and the overall is 0, then this part, which is basically considering a real substance, the del Q ref by T also has to be 0. So, therefore, this del Q ref by T, whether you are using a different substance than ideal gas, is going to be 0. Right? This is one way of again proving the same idea. Now comes a very interesting part of the second law, and that is called Clausius inequality. Right? Where the Clausius inequality states that there is this ds which is greater than or equal to delta Q by T. Already we know now from the second law definition and for the reversible process that ds equals to delta Q reversible by T. That means in the inequality case, the ds has to be greater than delta Q irreversible. So delta Q IRR is delta Q reversible, right? Right. Now how do we prove that? Now, as you see, the first law is also valid, that is principle of conservation of energy. So the change in internal energy du equals to delta Q plus delta W. Now I can tell that this delta Q is some arbitrary, say for some irreversible process, and this is also for some irreversible process. Okay, I can tell. But delta Q IRR plus delta W IRR, but du is equals to also, if I think of this as a reversible thing, so you have du equals to delta Q reversible plus delta W reversible. Right? So both are correct, right? If I replace delta Q reversible by delta Q irreversible and delta W reversible by delta W irreversible, then the point is that the point is that the du in both cases we can always have this equality, right? Du equals to delta Q plus delta W for any type of process, whether it is a reversible or irreversible does not matter, but delta Q plus delta W for any process should be having the same du, right, because of the first law. So this equality holds. We assume that this equality holds. We want to show that the Clausius inequality statement is correct. What does this mean? See, is that ds is equal to delta Q reversible by T. However, ds is greater than delta Q reversible by T. Now think of this. What we want to tell here is more in terms of watt. So the watt done by the system during a reversible process, which is minus delta W there, or you can write mod of delta W there, is always greater than for an irreversible process. So delta W rev is greater than delta, or we can write, see, what we are telling is, this is what done by the system is negative. So delta W rev, so this basically means minus delta W reversible, right? That is the work done by the reversible process. This is work done by the irreversible process. Let us call it delta W IRR. Now what we are telling is delta W reversible will be greater than delta W irreversible, but it will be equal to, so that's why I do not want to put the subscript IRR, right? We do not want to put the subscript IRR, that when delta W reversible equal to delta W, in such cases, the delta for this particular arbitrary process also, it's a reversible. It has to be a reversible. The equality sign only holds for reversible processes. However, for irreversible processes, delta W reversible, that is the heat, the amount of watt extracted from a reversible process is always greater than the amount of watt extracted from any other process. Right. So if we have this inequality, we can also write this as delta W. Right. We take delta W on the left hand side. So you can write this as delta W minus delta W ref is greater than or equal to 0. Right? Again, equality holds only for when both delta W and delta W ref are reversible, represent reversible processes. Now, what is delta W minus delta W ref? If you see delta Q, so if I write this, so if I just remove this thing, so we have delta Q plus delta W is delta Q ref plus delta W ref, right? So that's what we have, right? We have written that. So delta Q plus delta W equals to delta Q reversible plus delta W reversible. Therefore, we can tell from this relation that delta W minus delta W reversible, right? If I take delta W reversible this side and I take delta Q the other side, so then equal to delta Q reversible minus delta Q. Now this has to be greater than or equal to 0. So delta Q reversible is greater than or equal to delta Q. So delta Q reversible by T is greater than or equal to delta Q by T, where delta Q by T is for an arbitrary process. The equality holds again for the reversible process. Now delta Q reversible by T, what is the definition of delta Q reversible by T? That is nothing but ds, and ds that means is greater than equal to delta Q by T. That means that is the Clausius inequality. So ds, again just to recap, ds is delta Q reversible by T. For any other process other than reversible, ds is greater than delta Q. Any other process means which is not reversible, so that means it's reversible. I can write this subscript of IRR, which is a reversible process, and we can tell that this is what is Clausius inequality. Now, what is the meaning of Clausius inequality? Clausius inequality basically tells you the directionality of a process. For example, heat will always flow from a hot body to a cold body, not vice versa. Means from a heat will not be, unless you have connected an engine or fitted an engine, or you are making a heat pump where you have something where work is being done on the system. You cannot have spontaneous flow of heat from cold body to hot body, but you can have it from hot to cold, right? How do you prove that? Using Clausius inequality. As we know that ds is greater than equal to delta Q by T, and this, now if you have hot body, so you have say delta QH that is coming out of the hot body, and delta QC which is entering the cold body. So I can, hot body is at temperature TH, so what we are telling, TH is greater than TC, and delta QH is the heat transferred from the hot body, and delta QC is the heat transferred into the cold body. So you have ds is greater than equal to delta QH by TH plus delta QC by TC, and delta QH is basically leaving, right? It is leaving, so delta QH has to be negative, right? It is leaving the system, right? It is not heat input, but it is heat output from the hot body. And delta QC is entering means it is positive, right? So delta QC is minus of delta QH. That's the point. So now ds equal to delta QH by TH minus delta QH by TC, or if I take delta QH common, which is negative, remember this is negative, you have 1 by TH minus 1 by TC. Now if delta QH is negative and ds has to be greater than, right? ds has to be greater than delta Q by T, then if ds has to be greater than or equal to so delta QH is negative, so 1 by TH minus 1 by TC also has to be negative, right? Now 1 by TH minus 1 by TC have to be negative, means it has to be less than 0 or equal to 0 in the equality case. Now if that is so, since TC is less than equal to TH, since TC, so if 1 by TH minus 1 by TC is less than equal to 0, you can immediately see 1 by TH minus 1 by TC is equal to THTC. This is TC minus TH. Now TC is less than TH. Therefore, this 1 by TH minus 1 by TC has to be less than 0. Right? Only when TC equal to TH, then only it is equal to 0. So 1 minus 1 by TH minus 1 by TC in general will be less than 0. Or TC has to be less than TH. So for the ds to be greater than equal to 0. That means heat will always flow out of the hot body into the cold body, right? So this is the directionality we have assumed, and this direction is correct. If you would have done the other way, ds should have been less than 0, which is not possible. ds has to be greater than 0 according to Clausius inequality, which again comes from the second law. Okay, second law basically defines the direction of the natural process. Now you will tell me, okay, what happens in an isolated system? For a completely isolated system, you can have subsystems, but we have already shown that delta Q in an isolated system, the delta Q, right, the amount of heat input or output is going to be equal to 0, right? Because it's an adiabatic system, it has adiabatic walls, right? It cannot exchange heat with the surrounding. So delta Q is going to be 0, but depending on whether the process is, so if the process is a reversible process that is happening in the isolated system, then ds equal to 0. This is for reversible processes. But if it's a natural process, an irreversible process, then ds has to be greater than 0 or spontaneous processes. This is basically for isolated system. So remember, for an isolated system, your outside, basically your wall that separates the system from the surroundings is adiabatic. Now if it is adiabatic, delta Q is 0, but ds is greater than 0. So entropy does not decrease. So this is the most important part. Entropy does not decrease in an isolated system, but it increases in an isolated system when there is a spontaneous change. If there is a spontaneous change, that means a spontaneous process or an irreversible process, then ds does not increase, but it increases, right, in an isolated system. However, ds can be equal to 0 for processes that are not spontaneous and reversible. Now let us think of this example that we are talking about 100 degrees Celsius and 1 atmosphere pressure, and we are talking about this particular process. Water liquid goes to water vapor at 100 degrees Celsius. Now remember, water vapor and water liquid are at equilibrium at 100 degrees Celsius, because if you look at, say for example, you take a pot with water and you put it on a burner and you raise the temperature to 100 degrees, you will see at 100 degrees, you will see these bubbles that are coming out, right, inside the water, and this water is started boiling, right? But you will see that water is still remaining, right? You are not, if you remain exactly at 100 degrees Celsius, you will see there is an equilibrium between liquid water and water vapor, right? Because that is the transition temperature at 1 atmosphere pressure. Again, if I change the atmosphere, if I change the pressure, then water can boil at a different temperature, right? So either it can, depending on the pressure that the system experiences, water can boil at a lower temperature or at a higher temperature, right? So it depends on that. So this is a phase. So basically, if you look at that, this is a transition temperature. Transition temperature is the temperature at which water in two states, the liquid state as well as the vapor state, are in equilibrium, right? So at this transition temperature, any transfer of heat, right? If I want to transfer heat so that water liquid goes to water vapor, okay, this heat transfer is reversible in this way that I can also think of extracting heat in such a way, reversibly, in such a way that water vapor condenses to liquid water, right? So at this temperature, right? So basically it's a transition temperature. So at this transition temperature, since both are possible, all the transfer of heat is going to be reversible. Now if that is so, delta Q reversible, again this is at constant pressure, right? So as you know, delta QP, these are right, delta QP is nothing but delta H, right? So at constant pressure, what you are basically telling is this is not correct. You have to write delta Qp equals to dH, right? The differential. So you are telling, so basically, if I think this way, Q reversible, so that means Q reversible, Qp reversible should be equals to delta H. Now but Q reversible equals to T delta S transformation, right? We can write delta H transformation equals to T delta S transformation, right? So as a result, delta S transformation, that means change in entropy at the transition temperature, is basically nothing but delta H transition by T, right? So this is something that is very, very important. So as you know, Q plus W equals to delta U, right? So and what I'm talking about is, so W, so this is like Q delta, yeah, so Q minus P delta V equals to delta U. Now Q equals to delta U plus P delta V. Now that is at constant pressure because there is no V delta P. Delta U plus P delta V. So as you can see here, and delta U plus P delta V is nothing but delta H at constant pressure. Right? This is U at constant pressure. So this is equal to delta H. Now Qp is also basically the same, right? So because if the heat transfer is reversible, right? At transition temperature is reversible, right? Heat transfer is reversible. So this is Qp reversible. So this is reversible. So if this is reversible, then it is also equal to T delta S. So delta H equal to T delta S at the transition temperature TTR. So basically what we are telling is delta H TR. TR is at the transition temperature, or delta H transformation is equal to T delta S transformation. Delta S transformation is the entropy change associated with transformation, and therefore delta S transformation can be obtained if I know the enthalpy of transformation and I divide it by the transformation temperature TTR. Okay, so that's the idea. So if that is so, let us now, so basically as you can see now that the enthalpy of transformation and entropy of transformation are related, and the relation is basically based on the means is such that delta H transformation is nothing but delta H transformation by T transformation. Now think of this, let us think of another problem, right? We can think of this one problem in this same line. So we are talking about calculate the change in entropy when an ideal monoatomic gas at 30 degrees Celsius and 1 atmosphere pressure is allowed to expand, right, from 0.5 liters to 1 liter and is heated to 100 degrees Celsius at the same time. Now you can think of this. So it is first allowed to expand from 0.5 liters to 1 liter, where you are keeping the gas at 30 degrees Celsius and 1 atmosphere pressure. Right? So reversible isothermal expansion at 30 degrees Celsius is the first process. We can think of this as two processes. And the second process is basically heating of the gas at constant volume. Right? You are just heating the gas at constant volume. And we are assuming the gas to be ideal and monoatomic. Right? So that means we are assuming this equation PV equals to NA. Now, if you see this, you have ds, which is nothing but delta Q reversible by T, right? This is from second law, right? Second law is giving you this. So delta S, if I know this, so I can write integral ds equals to integral delta Q ref by T, and as I told you that this is all state function, so I can take state I and then state F, right? That's what I have done. Right, you can see the equation here. That's what we have done. Now remember this is so what we are talking about is reversible isothermal expansion at 30 degrees Celsius, right? So we are telling first that temperature is constant, which is equal to 30 degrees Celsius. So delta S then can be written as the integral basically is delta S. The integral is basically going to be delta S is equals to 1 by T delta Q reversible, and delta Q reversible integral is nothing but Q rev by T, and this is basically, if I look at it, it is going from I to. Now, as you can see here, we told it's an ideal monothermic gas, right? We have this reversible isothermal expansion. Now, in this case, the change in internal energy, du, right? There is no change in temperature, right? There is no change in temperature. Temperature is constant. But du for an ideal gas is CVDT, for example, right? So there is, if there is no change in temperature, or if there is no change in temperature, then du is going to be 0, right? If du is going to be 0, then delta S, that then Q reversible is minus W reversible, right? So first of all, delta S equals to 1 by T I to F del Q rev, which is Q rev by T I to F. Now comes the part where the temperature is now at 30 degrees Celsius, because we are keeping isothermal expansion, right? Or isothermal 0.5 liters to 1 liters, right? This is a reversible isothermal expansion. Now, if I am doing that, temperature is constant, and we have to find out what is Q rev. Now, Q rev is nothing but, as you can see, because there is no change in internal energy, and delta U equals to 0 equals to Q rev plus W rev, and therefore Q rev equals to minus W rev. Rev means reversible, rev means reversible. I am repeating the words just so that you become more and more familiar. So rev basically denotes reversible, and this is basically minus W rev because delta U is 0 because of the constant temperature. Again, delta U is 0, T equals to 30 degree Celsius constant. So this is one sub process, right, where we are talking about reversible isothermal expansion from I to F. Now minus W rev, and W rev is nothing but integral PdV, right? W rev is minus PdV, integral minus PdV, but there is a minus sign here, so minus minus becomes plus. So it is I to F PdV. So again, we are talking about ideal gas. So PV, so you are telling that P is nothing but nRT by V, right? That's what I have written. So, but T is constant, R is constant, N is constant. So, nRT T by V. So, this is basically nRT ln Vf by Vi, right? I and F of the initial and final states. So, now if that is so, then delta S is Q rev by T. So, 1 by T, there is a 1 by T, as you can see here. Then nRT ln Vf by Vi, right? N is the number. So, we are talking about 1 when an ideal monothermic gas, right? So we have not indicated N. So that's not a problem because we know the pressure, right? Initial pressure, right? The step at the initial step, we know the pressure, we know the volume, we know the, because volume is 0.5 liters, we know R, we know the initial temperature also, which is 30, right? So basically, as you can see here, that for the process number 1, sub-process number 1, right? So that's why I have given this is equals to PIVI by TI, right? N equals to PIVI by TI. PIVI by TI, there is an R missing. So there is an NR, right? So because there is a R here, so N equals to PIVI by RTI, and R cancels out, so this becomes just PIVI by TI. So yeah, that just becomes PIVI by TI ln Vf by V, right? Now, what we are telling in step 2, right? This is the step 2. So this what we did first is step 1, right? In step 1 is what we did. So let's call it instead of 1, let's call it step 1. Okay, now if you have step 1, now we are looking at the step 2. What is step 2? Step 2, you keep the volume constant, but you increase the temperature to 100 degrees, right? From, right, that was the, so, and then heat it to 100 degrees Celsius at the same time, right? We have just divided into sub-processes for convenience. Now, here QREF is going to be, so volume is constant. So, if that is so, QREF, okay, equals to delta Q, so integral of delta QREF, which is integral of du, because we are no longer, volume is constant, so PdV, in this sub process, PdV is going to be 0, right? There is no volume change, right? The volume is constant, so you have delta QREF, which is basically integral du, and du is nothing but NCVMPT, right? CVM is the molar heat capacity at constant volume, and which from equipartition theorem we already know is nothing but 3 by 2 N kV, right? So which is like 3 by 2 R, right? So now you have delta S for subprocess 2. If I am looking at subprocess 2, you are basically looking at, so QREF by T, which is integral Ti to Tf du, right? So that's what I am looking. So it is basically du by T, and du is basically NCVT, and N is again Pi Vi by RTi with 3 by 2 R again gets cancelled here, as you can see, and you have dt by T. So I can write Pi Vi by Ti and then Tf by Ti whole power 3 by 2, right? Because this 3 by 2 R came because CVM is basically like molar capacity. CVM denotes the molar heat capacity. Right? So you get now delta S total, which is the delta S for the subprocess 1, right? You just now add it, and delta S for subprocess 2, so which basically becomes Pi Vi by Ti ln. So you have in the first case ln Vf by Vi, right? You have ln Vf by Vi. This is equation 1, and you have now equation 2. Now you add 1 and 2, then you have Pi Vi by Ti. You just do the simplification, you get ln Vf by Vi, Tf by Ti whole power 3 by 2, and you can also now plug in the values and check whether delta S is greater than 0. Delta S has to be greater than 0. Now one thing, this is all fine. Now how do you measure entropy? How do you measure entropy? Okay, so there are various ways to measure entropy. So one of the ways is, first we measure enthalpy, and we know that enthalpy, if I know the enthalpy, I can basically relate it to entropy. Okay, so that's what I will try to do, because one of the ways you could immediately see, say for at the transition temperature, delta H transformation, if I know the delta S transformation is nothing but delta H transformation by the temperature of transformation, right? Now, you can understand that entropy measurement again is indirect, right? They are directly measurable quantities. If I tell these are directly measurable quantities, directly means using some instrument. So we can measure CV, we can measure CP, like this is heat capacity at constant volume, heat capacity at constant pressure, then thermal expansion coefficient, then isothermal compressibility, even temperature, pressure, volume, all of these can be measured directly. However, if I want to measure enthalpy or you want to measure entropy, then basically we use something called calorimetry. So here, for example, I am giving an example of differential scanning calorimetry. Okay, so it's controlled by power. So what we are talking about is, if you look at this very simple example here, you have the sample for which you require some properties, right? You want to do calorimetry, and here is the reference sample. Okay, and if you see both the chambers, right, where you have sample and when you have the reference, both are basically connected to a thermocouple, right? They both are connected to thermocouple, and there are these two heaters, right? There is one heater here, there is one heater here, right? So we are telling the temperature of the sample plus the reference are increased at a constant rate, okay, and that is called the scanning rate. Okay, so T0 is the initial temperature, say, then SR is the scanning rate, which is in Kelvin per second. So at this constant rate, you are increasing the so SR is the scanning rate, and so TT at any time T is basically T0, which is the initial temperature, plus SR times small t is time. Now, as you can see here, Cp itself may be a function of temperature. So, if I tell Cp is in general, Cp is what? Cp itself is equals to Cp. Okay, Cp itself can change as a function of temperature, right? Now, if tall Cp is not a function of temperature, whether it is function of temperature or not, it does not really matter. So, if it is a function of temperature, it becomes slightly more complex. But anyway, what I want to tell, we are increasing the temperature of both the sample and the reference at the same rate, right? We are trying to do that. So, and we want to maintain same temperature in both. How do I maintain same temperature in both? If I know that there is a temperature increase in one, then I want to basically just increase the power of the heater in the other, so that I can maintain the same temperature everywhere. So basically what I want to do, the process is to transfer. So what I am trying to do, so you understand. So say for example, you have the sample and you have your reference. Now you are seeing that the sample is basically losing, means it is trying to lose the lose some temperature, or it is lose some temperature. Then what you want to do is you are just using the heater here, so that again the sample comes to the same temperature. How do you do that? You want to transfer excess energy to or from the sample undergoing a physical or chemical process, right? So if it is undergoing, the sample is undergoing a physical process by which it is losing temperature, you want to transfer energy to it, so that the sample again is maintaining the same temperature as that of the reference, right? So if there is no physical or chemical change of the sample at temperature T, if we assume that there is no physical chemical change of the sample at temperature T, then, because if it is there, then you have to also think of the latent heat or the heat of transformation, right? If there is no physical or chemical change, then it becomes very easy, because you have the initial temperature as T0, and Qp is basically Cp times delta T, which is Cp times T minus T0, right? And delta T is nothing but T minus T0, which is basically SR times T. Now, if physical and chemical process, if this physical chemical change is equal to true, then excess heat transfer to maintain the same change in temperature in the sample as that the reference is basically Qp plus Qp excess, right? That is what you have to give, right? Because if there is a physical or chemical change, right? If that is true. So we are talking about no physical, if there is a physical or chemical change is true, if physical or chemical change is true, okay, then the excess heat transfer to maintain the same change temperature in the sample, right, to same change temperature in the sample as in the reference, basically tells you require this Qp, but there is also a Qp excess that is required, right? You require to have this Qp and this Qp excess, we call it Qp excess, which is basically equals to, now Qp is Cp delta T, right? Qp equal to, you have seen Qp equal to Cp delta T, but this Qp excess corresponds to some Cp excess times delta, right? So this is some excess heat capacity times delta T if there is a physical or chemical change, that is basically true. Now Cp excess is nothing but Qp excess by delta T, right? Or this is basically Qp excess by SR, okay, which is basically given by Joule per Kelvin. Now, if it is an endothermic process or an exothermic process, so what we are trying to look at is, if there is no physical chemical change, then this is nothing but Cp delta T. Now, Cp itself being a function of temperature would have complicated the process, but if you assume that Cp is not a function of temperature, for the temperature change that we are talking about, right, the temperature change, if we take the temperature change to be small and we assume that Cp is not changing with, in these temperature range, then you can write Qp equals to Cp delta T directly, which is Cp into T minus T naught. Otherwise, Cp itself has to be expressed as a function of temperature, and you have to find out the integral Cp dt, and where Cp itself is a function of temperature, so you have to calculate the integral. That's all. Now, but if there is a physical or chemical change of the sample, then you add this Qp excess. The Qp excess is related to Cp excess and the temperature difference delta T, which is T minus T naught, which is basically Sr times T. Now, if that is so, then Cp excess can be written as Qp excess by delta T or Qp excess by Sr. Now, if it is excess, we can tell, or this is the excess one. So, this is basically in joule per Kelvin. So, now if you see it's an endothermic process, then as you know, in that endothermic process, heat is absorbed, right. So, basically you will see a peak like this, right, it's a positive peak. And the exothermic process, you will see heat is released, so you will see basically a negative peak, right, in the for an exothermic process. Now, if you look at this, delta H is Cp excess times delta T, right. So, delta H is Cp excess dt integral T1 to T, right. So, T1 to between T1 and T2 is what we are doing, between two temperatures T1 and T2 is what we are basically looking at, right. T1 is your, say for example, the reference the initial temperature, and T2 is your final temperature. So, if I now integrate Cp excess dt, then what I get is basically the delta H associated with the physical or chemical change in the sample. That is how we measure delta H. Now, if I measure delta H, now you will tell, okay, you have measured delta H, so what? How do you measure delta S? Okay, that's very interesting. Now, if I want to measure entropy, we know delta Q is TdS, right, if it is reversible, right? Delta Qp reversible. So, what we know from second law? Second law tells you delta Qp reversible equals to TdS, but delta Qp reversible is nothing but P means constant pressure, so it is nothing but dH, which is equal to Cp dt. So, ds equals to Cp by T dt. Now, Cp is now, you can now think of this as like it's a function of temperature. So, A plus Bt plus C by T square plus dt square, something like that, right. We have some values, representative values for silver and nickel, okay, in different forms. Again, there is a temperature range that you have to give if you have such an empirical or experimentally determined expression. Then you have to also give the temperature range for which A, B, C, D, these coefficients are valid. Now, once you know this, you already know delta H, right? You already know delta H. So, basically delta S is basically, I can tell very easily. Now, if from this expression itself it is clear that from these two, from these relation, you can write ds equals to, right, ds equals to Cp by T dt, and you can just do now the delta S is integral Cp by T dt for a temperature range Ti to T. That's it. You can basically get delta S. Now, the delta S basically you can directly get from the delta H by T also. Okay, if I know delta H by T will give me delta S for the transformation. Right? This is how we can measure entropy. Now, if you see, there is one very interesting point here I want to tell. That is Cp, as you have seen from the Debye's theory, that Cp tends to 0, right? The heat capacity tends to 0 as T tends to 0, right? Now, we can also think of that from de Viry's theory that Cp equals to AT cubed is valid at low temperature till 0 Kelvin. At low temperature means temperatures below the room temperature. Now, if you see that Cp by T, if I plot against T, and there are these phase changes, so basically this is my solid regime, this is my liquid, and this is my gas. As you can see, Cp by T extrapolated, so at 0 it is 0. Cp is going to be 0 as T tends to 0. Now, Cp is going to be 0, so as T tends to 0, but T is not exactly equal to 0. So, we are basically looking at some extrapolation that we want to do. With the extrapolation is done with this relation, Cp equals to AT cube, right? This blue curve basically gives me that extrapolation curve, right? So, we use that. But you see, typically for a solid, the Cp is increasing with temperature, right? It increases till the melting point, right? This is your melting point. This is your melting point. So, if I have gone up to melting point, now you see Cp by T is discontinuous, right? It is discontinuous. Now at the liquid, again this is your Cp by T, and at the solid, this is your Cp by T, and at Tn, this is discontinuous, right? There is a jump, and then from this Cp by T again you come down, and then again there is a boiling, right? There is a boiling point. Now at that boiling point again there is a jump, and then you get what is called gas, right? So basically the Cp by T is going increasing. Now it goes, and then from solid, when it goes to liquid, there is a jump at that melting point, and again from liquid to gas, when it is going, there is a jump at the boiling point. You can easily understand this. Basically, if you Cp by T, again remember ds equals to Cp by T dt. That's what we have done, right? We have written the Cp by T dt. Now that means S equals to integral Cp by T, right? Integral of this terms. If I do that, you can see S, basically if you look at the curve S, again you have the solid, you have solid here, you have liquid here, and you have gas here. And as you can see, the entropy starts from 0 at 0 Kelvin, goes up, then there is a delta S melt, and then this delta S melt, there is a transformation here, right? So there is at melting point there is a transformation, right? This is the melting transformation. Solid is transformed to liquid. In this case, you are seeing a jump in delta S, right? There is a jump, and why is there a jump? Because you see, you are adding heat to solid, and then at some point the solid has changed to liquid. You just go above Tm, the solid has changed to liquid, right? So now the liquid, again there is this entropy change, right? The entropy change is higher than that in the solid, right? The entropy itself is higher than the solid, and then again at boiling point where the liquid has to transform to gas, again you see there is a jump in the entropy, and that is the entropy of transformation, right? There is this delta S transformation here. So this corresponds to delta S boiling, and this is the delta S melt, right? And right, this is delta S boil, so you can see that. And again for the gas phase, definitely entropy is much higher than in the solid phase. You can immediately see that, and you can appreciate that the dispersion will be much more, or the number of energy states that will be accessible for gas will be much more than in the solid. Solid is much more compact than gas, right? So as a result, the entropy of solid is in general the lowest, then comes liquid, and gas has the highest entropy, right? And remember, these jumps in the entropy of transformation or heats of transformation, these jumps basically tell you that there is a transition that is taking place. I will also define later the order of transition. So I will end here today, and we will try to continue this topic further in the next few classes.